Alright, hello everyone. It's February 15th. I'm doing a bit early today, and I have a hard stop at 11 p.m. Well, today, two main things happened today. First was I was answering a question on Stack Overflow about plotting 3D in Matplotlib. I love Matplotlib, and this question is interesting. It's just a very standard thing, like when you learn calculus, right? You have a curve and you want to rotate this curve along an axis. Usually it's a curve along the x-axis. You rotate it, right? And then the curve is it's a quadratic equation, so when you rotate it, it becomes a cone, something look like a cone, right? That thing. I was like, oh, that sounds interesting, and I took a look into it. Man, it's not as easy as I had expected. And the rotating thing, like how it makes sense in Matplotlib, how they do it, it took a while for me to click, and finally I was able to do it. I think the trick is to think in terms of the spherical coordinate. And at certain times, the Cartesian coordinate is not the best, not the easiest to use. You have to go with, something else, and that something else is the spherical coordinates. And I read an article about what spherical coordinate is, and then, man, it's really helpful. And then I was able to solve that, and it gave me an idea. Can I write a generic function, right? A generic way to, given any curve, right? Given any curve, we can restrict it, like any curve that starts from zero, right? That starts from zero, and we want to compute it. We want to draw this rotating thing. I want to see if it's possible to do something like that. And the way that the function that I wrote right now can handle it, if it's only the curve only has one root, the function has one root on x-axis. If it has multiple, things will be a little bit more complicated. But I think if you do really have multiple, you can just segment it, which I think is perfectly fine. All right, I think it's perfectly fine. But yeah, anyway, it'll be interesting to see, right? I'll be interested to see how other people can use it. I might write something like an article and stuff. That'll be fun. Help me understand it better. All right, so that's that. And the second is I got a Valentine's Day gift. Guido Escher Bach. So I've heard about this book and been recommended to me by my advisor, by my advisor mainly, because he went through all this, and then he said, you should take a look at this. And Lord, I just got it, and I flipped through it. I have no idea what this book is about. A metaphorical fugue on minds and machines in the spirit of Lewis Carroll. Lord, this is a thick book. Like, as thick as it can be. I don't even understand. I mean, in total, it's more than 700 pages of pure text, and then weird pictures and a lot more. There's always this Achilles and tortoise thing, and crab, recurring characters. I have no idea, no clue at all what this is about. I mean, I don't even have a table of contents. Does it have a table of contents? Well, the prefix is oh, I see. Prefix 23 pages prefix, and then a content. Part 1 GEB, part 2 EGB. So GEB refers to Guido, Escher, and Bach. EGB is the title, Eternal Golden Braid. I just don't know what that means. 20 chapters. Oof. I don't know, man. Are you ready? Are you ready for this? This is a tome. This is freaking tome. Cover to cover to read this, Lord. Yeah, I guess. First published 1979. Johann Sebastian Bach. Yeah, I'll do it. I think this book probably take months, maybe 2 months to finish. If I ever finish. Alright, so that's that. Alright, enough of this. Well, we're on a roll. All easy questions. Solve this, and I'm gonna go through this one. So I read the solution last night after finishing with everything, and then yeah, I have a better understanding of this. This guy's method is the one that I want to use. It's really brilliant, so we're gonna go back to this. All right, let's solve this one first. Given route returns maximum depth. Number of nodes along the longest path from root node down. So this is 3, 1, 2, 3. Okay. So maximum depth. If not, root return 0. Otherwise, return max self.max depth root.left. Self.max depth root.right and plus 1. That should be sufficient test cases. Oh, across, that's about a year across these two. Curious of my previous solutions. Just curious. Huh, 104. Attack on Titan. 104. Yeah. Yeah. Okay, so the idea is, wait for it. So what I thought was correct, but it's just, you think something's correct, it doesn't mean that you can have a good implementation out of it. So this question, and this, it's very well put, that it's almost exactly the same as this one. In the binary tree, find the maximum path sum. And here is the same. We want, it's not a binary tree, but it's still a tree. So we want to find the maximum path sum, except that the path sum has a little bit difference, in which we're not taking the entire path, right? So because on one side, because we have analyzed that, we know that the largest path is going to be from a root all the way to the hub. We call it a hub, right? So it doesn't reach a node. So that's the one side of the path. So we can say, doesn't matter how you root the tree, we root it anyway, right? Let's just say root it this way. Then for each node, there's a possibility, right? The answer goes through it, right? The answer goes through it. So for the answer to go through this one, then the answer must be, right? If this is the answer, on the left side, we pick the longest path, and on the right side, we pick the longest path. Not the longest, the maximum path. And when we do left plus root plus right. And of course, because we have this requirement of one side has to have no leaf, so there are two situations. The maximum on the left with the leaf plus the maximum on the right without leaf, or the maximum on the left without leaf plus the maximum on the right with leaf. And that's it, right? And if it doesn't work, we just traverse the tree. And they might ask, what if I am on a node, like a child node, and it turns out that, like if we see this child node, this is a root, it turns out the solution is its, say, left subtree and its parent and a sum tree, like related to the parent. Now, this is definitely possible. But if that is to happen, it will have been taken care of when we look at its parent, right? Well, if the final solution is something go up, like say to 1, and they have to go to 2 and then somewhere else, then that solution will have been found when we're taking a closer look at 2. So we just need to go a very straightforward DFS. And that's it. That's all there is to it. It's just a DFS. And at each level, we need to find the left max from the right max and then add it together. And that's it. That's basically it. Now, that's one thing to consider is, like, it doesn't really matter. You can just DFS down. It doesn't really matter if the solution is going above. As long as you can keep the maximum, you can keep checking the maximum at every single level, then that'll be fine. And the second thing is, because this is not a binary tree, while question 124 is a binary tree, you will have bunch, right? For each one, you have bunch of children, right? So if you only have 2 children, it's very easy. You can say, okay, I can say with left tree on left, with leaf on left, without leaf on right, or without leaf on left, or with leaf on right. 2 situations. But now you have so many children, which one to choose to have the leaf, which one to choose to not have the leaf. Now, it turns out we don't have to worry about that, because all we need to do is to keep track of the maximum. Let's say on all the, let's say we have like 5 children, right? And then when we do the first one, we'll set, for each one we have, for each subtree we have 2 values, the max with leaf, max without leaf. And then we see every single child as the right one. So we need something on the left. So for the first one, there's nothing on the left. We just set it to 0. It's perfect. It's fine. All right. And we now want to, move on to the next one, right? To the next one. Actually, if it's on the left, if it's the first, we probably should only take, the one without the leaf. Because if we take the one with the leaf, we have a possibility. You know what? It's okay. We can take both. Yeah, and if it's here, if it's on the root, then we just make sure the one we take is not a leaf node. Yeah, we just we start with the one that's not a leaf node. Then we can just take all the way down, right? We take all the way down, and then as we go through, we keep track the max on both. So every time we check the new one, it's going to be the max of what we have considered before with the current max, and the other max to consider before with the current one. And that will cover all the cases, because it doesn't matter, right? It doesn't matter which one, because at the end of the day, we just, among all of these, we want to find the one with the max left and the max right? The max children, max other children. So it doesn't matter if we keep track of the max along the way, and then we go to the new subtree, and then we find the max. The solution will happen, right? The solution will be some max on here, right, plus some max on the other side. If we keep track, right, if it's this and this, then we just, keep track. So that's kind of the idea. So I'm gonna go do this. Hopefully it's not gonna be too painful. And after we handle this, this is gonna be going to nightmare. Did not solve this, but I did see that the solution must be a path that must be a path, right? Must be a path that does not end. Must be a path starting from a node, starting from a leaf, but not ending in another leaf. The best way to think about this is from this post. Yeah, we're gonna have to reference this post. The author correctly observed that this problem is almost identical in its core to 124. We can simply, right, DFS this tree at any routing, well, preferably at a routing that is not a leaf. Then we can guarantee, right, that the solution, right, must be a path that goes from somewhere on the left subtree of a node through the node and end somewhere on the right subtree. Thus, if we can find the max path on the left, the max path on the right, we will have a candidate, right? We'll have a candidate path rooted at the current node. We just need to go through this for every single node. They're treating every single node as the current root node and keep track of the max path sum at each node. The only difference between this problem and 124 is that this tree is not binary. The only differences, right, are that one, this tree is not binary, but it is not difficult to overcome this small complexity. Two, the path has to be with leaf on one subtree and without leaf on the other, which means for each node treated as root, we have to find two values, right? One is the max path starting from the root to the leaf containing the leaf. The other is the max path starting from the root but does not end in a leaf. Yep. What else? All null values are positive. All node values are positive, which actually makes this problem a bit easier. Okay, that's about it. Let's write it. Let's write it. I'm excited. All right, we need a graph. I need a graph. All right, we're gonna find a root. It has to be someone that does not can say root equals 0 while len graph root is larger than 1, is smaller than 1, root plus equal 1. Smaller equal to 1. Do I have n? My root smaller than n, and so we pick root that is itself not a leaf. Okay, now we can do def DFS current, right? So we can say node and its parent, and then return a tuple. DFS root -1 return self.res. Where's your self.res? All right, so this is what we need to do. So root, right? And we shall say when you are a leaf, right? When you are a leaf, there's no way to go. So you should return. What do you return? Containing, I can say, right, the return value is max path with leaf, max path without leaf. Okay, Therefore, if the node itself is, I will always do the max path from me, right, with a leaf. Basically, everybody that with a leaf, the max path. So we have two things, right? So max leaf, max no leaf, both starts with 0. And we're coming from me, I'm the node. Then I need to go through all my children. Let's say for child in graph node. If child is not equal to parent, okay, then we can say DFS child. This will give the sub max with leaf, sub max no leaf, right? This is on the child, we have 2. And we have max with leaf and max without leaf, just along the way, right? Along the way. So in that case, now we can say the max with leaf. So we can say self dot res shall equal to max self dot res with max leaf plus price node plus sub max no leaf, right? That's one of them. Or actually we have 2 scenario. One is this, and the other scenario is max no leaf plus price node plus sub max with leaf. Let's update that. And then max leaf. Did I say left? Then we say max leaf shall equal to maximum max leaf and sub max leaf. Max no leaf is maximum, max no leaf, sub max no leaf. So keep updating them once we're done, and then return max leaf, right, plus, so max leaf is my left child. Max without leaf is going to be my right child. And both need to add. So max leaf plus price child, right? And max no leaf. Now that is going to be interesting because I cannot add. I should, but I cannot. It depends on whether I'm a leaf node. So we can say this plus price child if len graph child is larger than 1, else 0. Actually, I don't need this. I just need this. All right. This is because if the child is the leaf node, then max with leaf is possible. I can do that. But max without leaf, it's without. So if I'm a leaf, so I should be 0, which means if I am equal to 1, then I should return 0. So that's that. Okay. Let's give this a shot. See how it goes. It's a very, very elegant solution. Okay, let's see if it works in edges. All right, let's see. too many value to unpack. Oh, I had one more, price. And I forgot to do this one. Come on, man. In edges price. Tuple is not defined. Parent, I forgot to add parent. Lordy. Oh, we fail. We fail. I think we have a little bit issue. That's okay. That's okay. We go on 27. 27? Which path give me 27? I mean, that would be 31. 27. And this one's 3. That's not right. I thought it's gonna be a... It's going to be a smooth run. It's not. Oh. Okay, so we can print node and print this. Let's check this one. Okay, node is 1. Okay, we start from 1. And then max, we start with 1. And then immediately I go to 0. Okay, so with 0 I return 1 and 1. That's not true. How is that 1 and 1? It should be 1 and 0. Oh, child. This is not right. There's a node. There we go. Typo. There we go. Oof. This is so good. This solution is so good. You can't even imagine. Holy crap. What the... What the hell is this? Edge case 2. 0 and 1. Huh. Should be 12, right? Oh, that should be 0. That should be 0. Because it's 0 and 1, we only have 2 nodes. If we only have 2 nodes, then everyone is 1, and then go, yep, and go to the other node. And when we do this, we have a child, yes. Then we go DFS child. We can get a child with width and and that will be 0. And at myself. That will be 0. And a max no leaf, that would be, first one be 0, plus myself, plus some x. So with that, I don't know why it's graph node. Why would it be out of range? Who is out of range? List out of range. What? What are you talking about? Node 2. Oh, because I plus 1. Root is equal to n. Ah. So I should have ended right here. So I can do is, if n is equal to 2, well, if n is smaller than 1, right? If n is smaller or equal to 2, then return 0. There we go. Let's give this a shot. Actually, I never know how it's gonna look like. I think it's a 0. Because 2, you can't have it. If 1, you can't have it. Oh, it's 12. What? There is a value for 2. Huh? Oh, yeah, there exists. It exists. The path is the entire thing. Minus this, so it's the bigger of the 2 nodes. How about 1? 1 is 0. Right? 1 is 0. If I do 1, there's no root. It's just 1 is 0. Yeah, 1 is 0. 2 is If I do a minus 1. Expected 12. Yeah, but that's still not right. This way of computing is still not right. Because you are here, right? You are at a node. I'm looking for the other one. And because I am a leaf. I am a leaf node. That's the thing. That's the thing. That's why I do this, because you cannot be a leaf node. So you know what? You know what? Three will definitely have. So 2 and 1 are edge cases. All right, so I think it'll be easier just to handle these edge cases here. All right, if n is equal to 2, I'll return the maximum of price. And all the other can be handled this way. Right? So that's what I'm going to change. That. Shall work. Very good. That solution's very, very good. I don't think that solution they handled this edge case. And it worked. I don't know. I want to try. It works. How? This is the same as me. This is the answer. This is the DFS function. Current max. Neighbor. Current max 0. Oh, including me or not including me, which means current max 0 is the current longest with leaf plus without leaf. Yeah, like better. Then root can be anything. And because of that, root can be anything. So max leaf and max no leaf shall be price, node, and 0. And this considers node. This considers situation. Yeah, that's very important. This considers the situation where node is a leaf. Right, so this is going to be max leaf plus submax no leaf, or max no leaf plus submax leaf. Yeah, because this is trying to find and max leaf is going to be max leaf submax leaf plus price node, and this max no leaf submax no leaf plus price node. The max leaf and max no leaf is including myself already, so then we don't have to do this. We just need to do max leaf and max no leaf, and then we're going to do 0. Sorry. Yeah. This is the solution. Exactly the same on this one. So max leaf is including me. Max no leaf is also including me. Okay, so yeah, that's it. Finally solved this problem after so many. No, it's a nightmare. Alrighty, that will be it. I will see you guys tomorrow. Adios.